Welcome to the last lecture of this class. Today I'm gonna explain you the SLAM front ends. So we've seen a lot of backends, we've seen a lot of way of finding a solution given a set of measurements, and now today I'm going to explain how to get these measurements. This is so we're using less time on this point rather than on the optimization, because this is very sensor specific. So I will give you a general idea on how things can be done. But then the implementation detail, it's very sensor specific, and it's really hard to put everything into one lectures in terms of sensors. So the second part of the lecture will just be a summary then, so it's probably going to be shorter than the usual. We might finish a bit earlier. And I also have the evaluation from you, and if you want, we can go through, you can give me more feedback, or if you don't want to stay here, you can just leave, and I just leave with the feedback that you gave me already. But we'll see it later on. So regarding front end, so what we've seen so far is the usual picture of graph-based SLAM, where we have the robot traveling around. It has different poses, different measurements here in orange, and it collects them over time. No? And we said that one type of measurements are the odometry measurements, which are the ones that robots collect while moving around. And then we said that there is another part of measurements which are the one that comes from loop closure activity, of loop closing. We said a lot of time during the lecture this word loop closing and so on. This whole idea here is that the robot goes around and then it does a data association between the things it's looking right now, so whatever is observing, and what you observed before in a different time frame. That can be 1 minute, 1 hour, 1 day, 1 month, 1 year. Okay? So the whole question of the lecture today is how to obtain those measurements, how to solve the decision part, which is the data association part that tells this place and this place are the same, and also how to compute a transformation between places so you can have everything that you need in this graph, the topological connection, which is the data association, same place or not, plus the metric information, which is the value that you put in the measurement itself. Okay? If you look back at the interplay we had before, we always said that we get the raw data. There is some front end which deals with the graph construction, and then it sends a graph made of nodes and edges to the optimization backend, and then you can have some feedback around that the solution from the backend helps the front end, and then it goes around and so on. And this raw data happens temporarily, so the robot moves and starts collecting and obtaining new data. Okay? What we're going to do today is this box. We have seen several ways of dealing with this box here. We have seen what if we just have a post graph, what if you have some landmarks, what if you can do it hierarchically, we did stochastic descent, and so on. Today we're going to see how to construct a graph. There are a few popular approaches for that, and they all go into the same umbrella of I have sensor data A, I have a sensor data B, and I want to answer two questions. Do those sensor data match, and what is the transformation between them? Most of the time when we talk about SLAM, we talk about we use laser sensor, so that provides you what we call a scan of the environment, which is a set of distance measurement from to closest obstacle. They just scan. That's where the name from, like horizontally on a plane, or there might be some 3D. They might have a lot of different beams, scans like this, but you get a lot of distance measurements. Okay, and when we talk then about matching, the idea is to align these points. But there are many other type of sensors. There might be cameras, there might be sonars we've seen, there might be any kind of way of measuring what's around us, magnetic waves, anything. And the popular approaches in this, you can see it in different families. One is dense matching. Dense matching basically says, I take the raw data of A, take the raw data of B, I define a score function that tells how good the match is, and then I'm trying to, let's say, find the best transformation that maximizes this cost function. Okay? Now it can be the overlap between the points, it can be whatever, if the intensity must be the same. If you have images, you just try to align two camera images and look if red goes on red, green goes on green, and so on. Now, this is something that it's very well defined. I have cost metric. I try all possible transformation. I get the best one. If you have point-based data, so if you just consider that you have like single points, that can be either from a laser measurement data where you have single endpoints from that, or it can be from camera. You get an image, you can detect some point in the camera, and once you have these points, they are like very easily isolated, and you can maybe match them and so on. No, but here it's just I have a set of point to point, and then I take 1 point from here, 1 point from here, align them. Okay, and then I found the best alignment and puts all these points on top of each other. So it's really a geometric alignment. We're going more into the geometric level right now. And the third one is what's called feature-based matching, where feature is a point with a descriptor associated. Okay, so when we talk about point to point, we just consider the geometric property, which can be xy or xyz, or maybe it's an oriented point, so we have xy, z, and the triangles, or whatsoever information we have. When we talk about feature-based matching, we have some geometrical information that could be pixel 3, 4, or it can be xyz in 3D world, plus some appearance information. That can be the color, that can be a descriptor, or it can be the curvature of the surface around the point, whatever you use to describe a local appearance of the point. And the reason why you want to use this is because you get better information to associate point with point. Okay? Now, we'll see today all of this, an example of each of these with a strong focus on laser data. Okay? But before going there, the first thing to ask is, those three approaches, they just take sensor data A and sensor data B and they match each other. But one sensor data is clear. It's what comes from the robot right now. The thing which is not clear is which are the other sensor data I'm comparing to. A naive approach will just take all the nodes in the graph and compare with all of them, but it might be so computationally expensive, they might be not robust enough. Another way of casting this problem is somehow, where do I want to search for these matches? Okay. Ideally, we want to use some information from the previous data, some information from the back end. No? So we have somehow a solution of the SLAM problem. We have an idea of how the world looks around us at some point in time. Then we get the new data, and we don't want to just throw all this away. We want to somehow keep it and have it with us. The way of keeping it is we do it in this way, that each of these nodes, these are different nodes in the graph, we know from the solution to SLAM that they have a certain location, a certain uncertainty. Okay? So we can just say, let's assume the robot is here. He has this field of view. Okay? And then I go from each of the node that I have in my graph and say, where is the node? What's the uncertainty of the node? And then I take the sensor, the field of view of the node itself, and I just somehow put all around in this area. And I get to a larger area. Okay? And this basically means I'm looking at which part of the environment could have been with high probability seen by that position in the world. Okay? And if I don't have any uncertainty, the only thing I can say is my field of view area, what I've seen so far. Since I have an uncertainty, I can be in different places around this place, so I want to just convolve this view around this uncertainty level. Okay? And now as an example, we get these two poses, B1 here, we get B2 here on the side, and then we in some way try to intersect this area, and if there is an intersection, we consider the pose as a potential candidate for matching. Now, we don't really do intersection between these spheres, but what we actually do is we have a bounding box around, we have like a circle around the view of the robot. So we say my maximum range is 30 meters. And then I just do a statistical search. So I know the pose of this, I know the pose of this with uncertainty. And then this gives me a distance. I add the field of view to this distance, and then I check my statistical table, chi-square test table, which is the probability that, which is if the distance is bigger than the most extreme event. And the most extreme event is something that happens with less than 5% probability. Okay, so that's a statistical test, it's a chi-square test that basically says, I have an experiment, I want to know how much mistake do I make if I just consider them as not being part of that. Okay, that's called type 2 errors. But in principle, there is a table, there is a set of values, and you just have to compare on these thresholds given a certain probability level. Now, in this case, this will probably be a potential match. This one will probably be not a potential match. Okay, so we don't need to do the full dense comparison of the sensor data here, but we just do it between these two guys. Is it clear so far? Now, another note on how do we compute the uncertainty. In principle, if you want to compute the real value of this uncertainty, we need to take the Hessian matrix of our optimization, so the one you've seen before where we take the Jacobian, transpose, the information matrix stacked with all the measurements times the Jacobian. This is the Hessian of our nonlinear least square problem. You need to invert that, and with this inversion you can get the block of the covariance matrix and you can get the uncertainty. The problem is that this is very expensive and you don't want to do it every time you get a measurement. So what a good approximation for this will be to compute a spanning tree or to compute a quick search on the graph. Okay, so the idea, it's what is called here Dijkstra expansion, and the idea somehow is that instead of having, just do it quickly like this. So imagine I have now a graph like this with some information in there, no? And the robot now is moving around and is here and is asking where do I want to match, which one I have to consider, okay? Now I can just solve the full graph before, invert, and I will get some measurements which are like maybe like this, it's maybe bigger, and so on, no? So the further I go from there, normally it's bigger. But it will be quite complex, computationally expensive. What I can do is, like, I just can go on the shortest path. By shortest, I consider as a distance the determinant of the information matrix on the measurement. So I go shortest in terms of the one that gives me more information, okay? Or let's say in this sense would be the 1 over the determinant. And then I just approximate this, let's say, by maybe a tree, then it becomes like this, no? Then I have maybe something like this, okay? And what we do, we just propagate the uncertainty linearly on these chains for each of these nodes. What will happen is that normally this uncertainty will be like slightly bigger, okay? And the reason why they will be slightly bigger is because we are neglecting some measurements. So we are neglecting this measurement, and this measurement, okay? So there is, you can prove that if you solve a nonlinear least square problem in graphical models which are tree-based, propagating the uncertainty on the different branches of the tree is equivalent to the solution to the problem. So in this particular case of SLAM, you can just prove it mathematically considering the nature of the relative measurements and how they actually, the implication that they have in the inference algorithm behind. We're not going to do it, just believe me, but basically optimizing a tree or going over the path comes to the same solution. And this is a rough approximation that if you are very close to the pose, it's not too bad, but if you are far away, it's getting larger and larger. The effect that you have here is that you have an estimate which is quite conservative. So the downside is that you're doing more matches, you're doing more evaluation of your dense matching than needed, but you're still not missing any potential good candidate, okay? So it's just a bit more expensive. And now comes the trade-off. Is it more expensive to compute the full solution and get less small evaluation? Or is it more expensive to compute an approximate solution and then doing more evaluation things? it's always depending on the problem. If you have, for instance, parallel computation available, then doing a lot of this comparison it's not really costly because you can do all them in parallel, assuming you have a lot of threads on a GPU whatsoever. Then it doesn't really matter if you add one or two more because they're anyway going to be in parallel. But in other cases where you have a very cheap to evaluate matching but very complex or very dense problem, this might be more computationally expensive than the other one. Okay, in principle, with a lot of nodes, this gets quite fast. So you don't want to invert matrices with thousands of elements because it's very expensive. If you are on a very small scale, it's okay to just completely solve it and then go for the real match. Okay? So, is it clear so far on all these things? Okay. Now, do you remember scam matching? We have seen it the one that had attended the Intro to Mobile Robotics should have seen it there. But we also saw it here briefly when we were talking about improved proposal for raw Blackwellized particle filters lab. No? We said one way of having a better proposal was to consider the matching of the data and then sampling from that. No? So scam matching comes also in here, and that's the way we abstract the data to a post-graph formulation of the problem. So instead of reasoning for all individual points and trying to match all individual points, we just consider poses where the robot is, and those measurements come from the fact that we are matching the data. Okay, so it's exactly what we did for the scam matching. The main one difference is that you see here, there is also an odometry part where I kind of cheated because I always told you when we go building the graph, we use the odometry. We actually never really use the odometry, but we also always use the like the improved odometry. Okay, but we don't have a data association problem because we know that those places are close by and those data are close by, so there must be an edge there. And in the worst case scenario is the odometry edge if I don't get any measurement. Okay, but if I get the measurement, I just get better estimate with the scam matcher. It just comes somehow for free, so it's a good idea to do that. If you want to do it everything in the proper one measurement per time, you will have had something like 2 measurements between the poses. This comes from the odometry, I just call it U, and then you will have another edge here that comes from the scans, S, and this will be then a hypergraph. You have much more variables, much more equations in your system. You can just merge them together, no? And exactly what we're trying to do there. You just like merge them together without explicitly putting twice into the graph formulation. Now, the idea here is that we want to find the maximum, the pose that maximizes the likelihood and is also consistent with the odometry. No? So that was the idea of scam matcher, and there are several ways of doing this. When we go on the full data association in the loop closing part, we normally do not really have this odometry, so we just assume that the robot stays still. Okay, so the odometry is the robot did not move between the 2 scans. And the idea behind that is that we try to align places where the robot was more or less around the same place, so we want to somehow find the place where it was the most close to some place before. And this will be like a displacement of 0, which will be the perfect. I'm exactly in the same position as before. In practice, what we do is we will initialize the scam matcher somewhere, and this somewhere comes from the previous solution of the optimization. So this will be somewhere around here. There's this guy, this whole configuration of the poses has a specific pose in the word. We have an odometry that connects this guy with this guy, and then we also have an absolute or a pose for the current pose. Okay, for the current robot, we have his pose in the same frame, and then we can compute all the potential odometry, but we just use it as potential initialization of the scam matcher. So we know where the robot is in the other view, okay? Because we just take it from the previous solution plus the odometry forward. Okay, that's needed because a lot of these alignments, they need to know roughly where the robot is to then work around. We'll see why it's the case. Now, when we have the next things to do, since we have we want to describe this matching and front-end point of view, we need to figure out what we need for sure. So the first thing that we need is that we want to have not only the pose, but also the uncertainty. So we don't want to just have the transformation between these two nodes, but we also want to have an idea of how uncertain this transformation is. And this part here is just saying that we take the data, we match them somehow, and we get a transformation. And then we want to evaluate how good the match is. And we also want to decide if we want to accept the match or not. Okay? The decision can be done on thresholding or can be a much more sophisticated decision. The easiest one is the percentage of the data point that agrees. No, like I try to take a set of points, I put them on top of each other, how far each point is to the neighbor, sum them up, this gives you a number, put a threshold, and find out if this is a valid match or not. This is, for instance, an idea. I have a pose here red, a pose here blue. Blue is associated with the black dots, the red is associated with the red dots. I found this alignment. I look at each point, I say, oh, they're pretty close by, that's not much further away, there is no real isolated point, just few of them in this part. I think it's a good match, I accept it. Okay, so that's somehow the reasoning. Now, for doing, so one example of matching, and now we're doing an example of dense matching, the first category of the three approaches I've seen before. It's what's called correlative matching, okay? And the idea of correlative matching is exactly the same idea of what I said. I try to look for how many points agrees, and I decide yes, no. It's just that it iteratively tries all possible transformation and within a certain area, and then it gets out which is the best one. It needs to discretize the XY translation, it needs to discretize the rotation part, and what it does is something like that. So here we can see, let's see how I can explain better. Each of these image that you see here is a different discretization of the orientation of the robot. Okay, so it will be something like the robot is here, or here, or here, 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 here. Okay, each of these small dot is the score of if the robot is in this position, this position, this position, this position, this position, and all going around. The idea here is that imagine this is the area I'm trying to localize or trying to match. I take one orientation, so I put the robot oriented like this. I have my two scans. I have a measure, which is just for each point, in this case, will be really like two images. Whenever there is white is +1. Whenever there is black is +1. And whenever there is a mismatch, it's 0. And you want to maximize this score. So it's really like what's called I think they use normalized cross correlation score here, but anything that says these two patches are the same, it's good enough. So that just has to have, the closer these two patches are, the higher should be the score. No? And it goes around here and tries all of them, and then it gets this image. This is a jet map. Means black is very low score, blue gets in the middle level of score, then it goes into the green, into the yellow, the orange, the red for different values. So red is very high score, good. It then rotates a bit, does it again, rotates a bit, does it again, and so on. And this you can easily implement on a GPU, very in parallel, because you have to do a convolution, and GPUs are very good in doing convolution between images, and you just need to define also that the convolution is in 3D. So it's a 1, 2, and 3 convolution, okay? And after you do this, you end up in, that's the best solution for my case, okay? So you will end up, this is the highest value from all the images. This means I have defined the x and y by considering the pixel in this image, and the theta by considering the discretization that I used so far. Okay? So it's really like a brute force approach. I try all possible solutions, and to make it efficient, there are two things that you need to take care is the search space. So how far, so let's assume I have one initialization. How far left, up, down I want to go, and how far from the theta I want to go. Okay? So the theta has a very clear defined border. It's between minus pi and pi, or 0 to pi. So you know that you cannot do, if you do twice the circle, you get actually the same orientation. But the discretization is also important. So when you want to do it 1 degree, 10 degrees, 20 degrees, this all affects the quality of the final transformation. So one of the problems, of course, comes from this trade-off. The fact that you need to do a lot of matches, and if you cannot do them in parallel, it might be very slow. If the accuracy is actually low with respect to the discretization, so the faster, the more coarse the discretization, the lower the accuracy. Okay, and the uncertainties are also slow to compute because there is no clear, explicit cost formulation, so you cannot compute gradients of this approach, or at least you cannot compute analytically any gradient of this approach, so you cannot propagate uncertainty from the sensor uncertainty to the estimation uncertainty, so you need to do it from the definition point of view. The definition of a covariance is the, the scatter of the error, so you really need to go around left, right, up and down to do a lot of samples around this best solution to then estimate a covariance out of it. Okay? So it's very expensive because you need to do a lot of this evaluation for the full correlation term. Okay? So that's some of these advantages. Any question on that? Okay. So the second class of approaches that I want to explain you today is what is called point-to-point matching. And there are also some variants of that that have point-to-line, point-to-plane, line-to-plane, line-to-line. So it's more on, I have a certain geometric feature, for now it's point. I have another geometric feature, which is point. I define a error metric between them, and then I try to align them in the best way possible. The most famous work is what's called the Iterative closest point algorithm, which it just iterates over the points, gets the closest point, and then by this association, he knows which is the best alignment that you can get, and iterates over and over the time. But the interesting thing is that the uncertainty can be easily estimated because once you find the solution, you have everything in an analytic form, and you can just propagate the gradients down there. You can, if you don't know where you are, you can actually sample. So what you can do is you can sample around the odometry, potential initial guess, initialize the ICP from there, and then take the solution that ends up in the lowest cost. This is to avoid potential local minimum in the cost function. So the idea is something like, what is the deleting thing? The idea sometimes, like, imagine I have a situation like this, no? That's my one scan, let's say, and the other one looks like this. Okay, very similar. This is just an example. Later on we'll see how to deal properly with these things. And imagine I might be around this area, okay, from my odometry uncertainty or for the whole projected uncertainty from my Dijkstra expansion or however I computed them. Then I can get one initialization here, and this, let's assume I am like this because then it makes more sense. So I get something initialized around here, okay? And I sample, I do the alignment, and I get somehow something like this, okay? That's quite good, it's very high. But I initialize another sample I get here, then it might be attracted to this other guy. So I might get something like this here, and then somehow like this, okay? Now imagine that the real one would have been like a straight line, so that we don't have uncertainty or partial visibility or so. Then if you then consider the value of the cost function, this will have a lower value than this one, okay? So, and this is because your cost function will then be somehow like this, and just have an idea, but will be something like this, and you try to maximize the overlap in there, no? And if you end up here, initialized here, you will converge to this part, because it's a local search. If you are initialized around here, you will converge to this part. We'll see in detail the algorithm how it works, but that's the idea of why you need to sample places there. Now, how does ICP work? We have 2 point sets, okay? The first point X set, the first point set X, second point set P, and each of them are just a set of points, XY coordinates or XYZ coordinates. And what we want is a translation and a rotation, so a rotation matrix, a translation vector that aligns X with a transformed P, okay? And we want to associate for each P the correct one, okay? So here we just assume that Xi and Pi are corresponding points, someone told us, and if we have these correspondences, we can solve this minimization problem in closed form, okay? How the ICP works, the key idea is that to get the correspondences, you can, for instance, try to trace all possible locations, and once you get them, the transformation will give you something like that. So it takes this, it rotates a bit, moves on top here, and it tries to make the best alignment possible, okay? Traditionally, correspondences are found by just, for each point, you look for the closest one. That's why the name is called closest point, iterative closest point, okay? There are several other ways of finding better correspondences. There are some shooting methods. There are some you can use, for instance, the features. Like if you have a descriptor, you can also weight this kind of appearance information in there. You might have surface normals, and you want to have the surface normal also to be well aligned and so on. But that's out of the scope. So for now, just assume there is a very simple routine. I just take the closest point and associate it with with the first point in the point set. Once you have it, one trick is to, we first compute the center of mass, okay, for each point cloud. That's just the weighted average, and the weights are now all the same of all the points, okay? So just a scatter point, we take the center of mass of one, we take the center of mass of the other. Once we have that, we can transform our problem by just subtracting the center of mass of both of them from the original cloud, okay? Once you do this, what happens is that you end up on a different problem, which is like this, and you can solve the full, you can get the rotations by just doing what's called a singular value decomposition, okay? So the whole idea is you can derive it on your own. It actually would be much fun, but if you take this expression, okay, and then rewrite every point with respect to the offset minus the center of mass, you end up in that you need to solve a problem like that, kind of, okay? So you end up that for solving that by getting this W, this will be your rotation matrix, okay? Once you have it, you will end up that, yeah, I'm just skipping the proof. If you want to have it, I can give you, you can just write me an email and I can give you some hints to some pointers to where to find the proof of that. But the idea is that once you have the thing built in this way, your rotational matrix is just this part, is the eigenvector, so they are the eigenvectors of the kernel and the eigenvectors of the image. And you then can get the translational part by just rotating the second set of points, and then just taking, that's then a linear problem, and you just can find the t out of that. And the solution, it's exactly this one. because it will come from, you will end up in something where here you have the mu, the transformed mu, and then you just need to find t. Okay? You have the mu, you have the transformed mu, you just get the t out of it, and it's just the difference between them. Okay? So in principle, what you need to know is you build the problem, you compute the center of mass. Once you have the center of mass, you can compute this. This x prime and p prime are the offset of each point with respect to the center of mass. You build this W matrix, and you do a singular value decomposition of the W matrix. Okay? So let's see how, so intuitively what it does is this. I have a set of points x, okay? I then have a set of points p. Maybe let's do bolts. When I compute the center of mass, somehow I get something like here, no? And something like here, okay? Then you can imagine that you compute the principal direction of this guy, no? Let's assume like this. And you end up with something like this. Then you get the principal direction of this guy, and you try to align them, okay? And this is the same as taking the outer product of the differences between the center of mass, so the outer product of each of these vectors, okay? So each of these vectors defines somehow a projection between them. You take the outer product, that's the projection matrix, you put all together, and you find which are the main directions. I don't know if this helps intuitively, but that's somehow what's happening in the background. Okay? And once you have the right rotation, you just find the translation vector. No? Our t. Okay? So I'm not going to ask any proof of these things. It's fine if you know that you can just put it in this form and then compute an SVD and you get the rotation matrix out of it. Okay? So these are the formula for the rotation matrix, the translation vector. You can also compute the minimal value of the error function in a closed form given all the things that you have. So this is easy to have it because then you can evaluate if a certain hypothesis is better than another one, no? In case we did the sampling around here. So you know if this is a better minimum than the other one. Okay? Okay, that's for the association. There is also a way of computing in closed form or analytically the uncertainty of the relative estimate. This involves the possibility of deriving, where is it? You just derive this. This is your cost function. That's what you want to minimize. There is something called the implicit function theorem. So your solution here is a minimum of a function. And by using the implicit function theorem, you can know which is the Jacobian of the minimizer. Okay? And if you know the Jacobian of the minimizer, you can just project it there. The way to compute it is just you need to compute the Jacobian of this with respect to the state and the observation, so with respect to R and with respect to X and P. And then you have this double chain of, because your uncertainty is in the X and your state is in the R, and you want to project the uncertainty of the error through the observation to the state. I'm not going to ask you in the exam, but I wanted to tell you that there is a way of getting analytically a covariance or uncertainty estimate out of this. And that's why it's actually quite useful to use it for computing the measurements, because you don't need to then evaluate everything around and then do some numerical computation of the uncertainty there. When we don't have known data association, we need to look for correspondences. And as I said before, the original way is just you get the closest point and you converge if either these are close enough, or another way of convergence is if the association do not change. Because whenever we don't change the association between points from one iteration to another, it means that the minimization part will give us the same solution that it gave before. Okay? Sometimes it might oscillate, so you might find pathological cases where it's like associating, always alternating between associations, so you will never converge, but you can easily spot these cases because your value of the error function is not decreasing or is oscillating, so just do some checks and you will spot these pathological cases. Okay, so summarizing the ICP, the basic ICP algorithm, we just need to determine corresponding points. We do it by considering from one point cloud of one set of points, the closest one in the other set. We have two formulas that tells us how to compute the rotation and the translation given this associated point set. We compute that. We transform the second cloud. We reiterate over and over. And if the error decreases, it's below a threshold, the correspondences do not change, we just stop. And then we output the final alignment. Once we have the final alignment, then we can do an external check from the front-end point of view to say, do we want to trust this alignment? Yes, no, and we have the external check on top that, for instance, says, this is the best alignment I can find, but it's still not good enough to be sure to include it in our graph. And not good enough means there is not enough overlap of the points, for instance, or we'll see later on can go to whatever different level of complexity on how to decide if something is consistent with the map that I built so far. There are some problems of ICP. One thing is that it's sensitive to the initial guess, and this is actually connected also with the local minima problem, because it's a local search problem, and if you have a cost function which has a lot of minima, according to where you initialize it, you will end up in one of them. One way of solving it is to do some sampling around there, so you will get something better, but you increase complexity in terms of time complexity because you need to run several ICP routine in parallel or one after each other to get one single solution. The other problem is that there are ambiguities in the environment, okay? And this is something that you cannot solve because we are always doing scan-to-scan matching. So if there are ambiguities, we are not looking at all at the other part of the world. Sometimes we can put on top something that deals with global ambiguity. We'll see a refined way towards the end of today's lecture. But you can also think of doing this analysis of the lowest cost, but do it for the all possible solutions that you get out of all possible alignments, and just select the best one out of all of them. This will remove some ambiguity because you will only get one measurement between two poses for one sensor data, but you can get lower accuracy because in principle you can get a very nice network of measurements. If you are like, this is the parts where the robot travels, then goes somewhere and comes back. One thing is to say, I just have a measurement between these two, and one thing is to say, I have a measurement between all of them. So these are multiple measurements that you can actually merge together, and you get much more rigid structure, and you get more accurate estimate. Okay, so these are a bit of a trade-off between the two. There is a way of getting most out of it. We'll see it towards the end of today's lecture. So the second thing that I want to explain is this feature-based matching. Feature-based matching solves, or at least addresses, these two parts somehow. So it gives you a better way of computing point correspondences, which in turn makes a better way of, it makes more robust to initialization, and also it removes some part of the local minima implicitly, okay? Because it just gets you closer to where you should be. And on another point of view, it's also very interesting because you can then abstract a lot of properties of either the environment or the sensor, and just having one framework again. By feature-based, we say that features are point-wise elements in the sensor data, so we just treat them as a point, and they have an associated descriptor in there. So we can do environmental abstraction, because here we have a very dense indoor environment where features might be the corners or some gaps or isolated pillars and so on. Or we can go outdoor where features are just tree trunks or might be poles or pillars and so on. And we can also do some sensor abstraction, because we can use laser where we get some data again at these corners. It's a point-wise feature with some descriptor. Or we can use cameras where we can say there are some point-wise feature in X, Y in the camera or in the projective space with some descriptor. And at the end, it doesn't matter if the descriptor is a set of numbers that comes from color or if a set of numbers that comes from appearance or shape, because at the end, you will use the same distance metric between the descriptor to associate them. Okay? So how does this feature-based matching work in practice? There are three main steps. One is that we first detect these features from the data. We describe these features that are detected, and then we do a matching between these feature sets, mostly based on appearance and geometric properties. Okay, so the one limitation of ICP was that the way we do the association between points was just the closest one, and now we do association between points that looks the same. Okay, so these associations are much better, are more robust to initialization, because they do not depend on that, it just depends on the local appearance of the sensor data around that. There are very popular methods, and there have been a lot of features developed over the time, both for laser, 2D or 3D laser, and for camera. So here is just a list of them. Flirt, Shot, NARF. So these two have been developed here in Freiburg. This one, Sift, Surf, Brisk, Fast. These two are Zurich. This one, UBC. So there's a lot of a plethora of that, and of course there is no answer to the question which is the best one. It always depends on the application, what you need, what you mean, what's your goal, which kind of data you have, and so on. But you can play around and look at them. How to do the matching? The most common or the most popular algorithm for matching this feature set is what's called RANSAC. RANSAC stands for Random Sample Consensus. So the idea there is that you have a lot of potential matchings from the descriptor point of view. Some of them are outliers, so are not good matchings, and some of them are actually inliers. Okay, and the idea is that you want to try to find some consensus between all potential point-wise, pairwise matchings, so that you believe that all of them are in the inlier set. Okay, there are 4 steps, and I'm trying to explain it, and just stop me if you don't get what I'm saying. The first thing is that you have to sample a minimal solution set. Okay, so the idea is this. I have a set of pairwise correspondences, okay? And this is my X, that's my feature set X, that's my P, my other feature set P. And it might be that each point of X has one or multiple correspondences, okay? And some of them might not have any correspondence, so we don't. This, for instance, is isolated, so we don't take it. And, okay, let's just make it like this. So you just do this matching, and then from this, each of these will be one potential point in your solution set. This will be another potential point in the solution set. This will be another point. This will be another point, okay? So everything that looks somehow the same, you want to consider as a possible association. So you don't want to throw it away. You don't want to just go on the most likely one, because it might be that it's not good enough. okay? And some of them might be completely rubbish, and some of them might be that in one of them is good, and the others are, of course, not good, okay? So that's the idea here. But you have a list of a lot of them, and then you have your alignment problem, no? So if you consider 2D alignment, you need to have at least 2 correspondences to get a full 3D, a full 2D plus or a rotation plus rotation transformation, okay? And that's your minimal sample set, okay? So which is the minimal number of these correspondences or these points in my solution set that allows me to give a solution to the problem, okay? So the minimum number of equations that I need to have to find a solution. And you don't want to have more than that, and we'll see later on why. Because then once you build a solution set, so you have a minimal solution set, you get the solution, and then you check how many of the others actually agrees on that, okay? So it's like an advanced way of voting, no? So normally when you vote, it's like there's a lot of people, and each of them vote to something. And then the one that gets the majority of votes win and is elected, no? In this case, we have another election. We are voting for the best transformation. And the problem is that we cannot, each single individual cannot vote for a transformation. And now we need to find the subset of individuals that can vote for one, okay? So you simply randomly here, take 2 of them, they vote for one, and then you check how many of the others agree on that. So right? And this is exactly what's written here. We get this minimal sample set. We compute the transformation out of it. We compute the inlier set. The inlier set is the number of other points in the solution set that actually agrees with that. And then if the inlier set is bigger than the previous one, we just update to say, I found a better solution. It's made out of these inliers and with this transformation. And you repeat. Now, the interesting thing of RANSAC, if you just look at it in this way, it's like, okay, I'm just randomly selecting transformation and I'm trying to find which is the best one. But when do I stop, for instance? How many iterations do I need? How am I sure that I found something which is reasonable? And the interesting thing of RANSAC is that you can reason probabilistically on the amount of inliers or the amount of outliers that you have, and you can actually come up with a number of iterations that you need to do for this, such that you are sure with a certain confidence level that you found the best solution given that the amount of inliers is this, okay? And there is a formula that tells you how many iterations you need to have. It gets complicated, but let's go now on let's assume that Q is the probability of an inlier, okay? So it says each point from this one, and I call point this pairwise association, is an inlier with a probability 0.1, 0.3, 0.9, depending on your problem, okay? This basically means that out of these all points, 70% will be inliers on average or so. This will be then the number of inlier the all possible k, and k is the minimal sample set, out of the number of inliers, okay? And then we have k out of the number of all potential points. This basically is the ratio of the minimal sample set, which are composed only of inliers, okay? And this is the any possible combination of k elements out of n, okay? So this is the number of outlier-free minimal sample set. This is the number of minimal sample set, okay? So I know for sure that this value here, this Q here, will tell me how probable is that out of a random sample, I get an inlier, a full inlier set. So a set which is not made out of outliers, okay? And that's important because if I get a set that it's made that doesn't have any outlier, I know that the solution I compute from that, apart from noise, is a correct solution. Okay, so that's the reasoning behind that. If you just expand this, you end up that this is the the real formula for getting up this Q, but we can actually approximate it if in this way, where we just take the ratio between, so the I, we just don't consider it. If n is very large here, I is close to 0, so I have a very small sample set. This has not much influence in here, and then we can just approximate it as the ratio between the number of inliers divided by the number of total points, so the probability of an inlier, and at the power of the minimal solution set. Okay, so basically we go from sampling with replacement, without replacement, to a sampling with replacement. Don't know if you know somehow the distribution, the urn, the whole thing of like you have a ball with a lot of color balls, and you take a red and the one, and there is one way where you say I don't put them back in, and one way where I put them back in. This is I'm not putting them back in, and this is I'm putting them back in. Okay, just to give an idea of what we are doing in terms of approximation level. If we have that, we can just compute the probability of the outliers in the minimal sample set. Okay, and since we want to have a minimal sample set which is 3 outliers, we want to have this probability to be less than a certain epsilon. Okay, so we say I want that the probability of an outlier in the minimum sample set be less than 0.05% or something like that. So a confidence value that we want to get. And if you do this, we can just compute which is the number of iterations, okay? Because this basically is saying, this is every time I try it out, outlier, try it out, outlier. And then since you have h iterations, you want to know which is the probability that all of them are actually with at least an outlier, okay? And you want to minimize that, and you just want to find which is the good h, and then you take the logarithm of this, you just solve this inequality, take the logarithm left and right, and you end up that h must be bigger than the logarithm of epsilon divided by the logarithm of 1 minus q, okay? So we have a way of computing the, let's say, the optimal number of iterations that given that we have a certain inlier ratio and that we have a certain target probability for how sure we want to be that we didn't make a mistake. Okay? So this doesn't tell us that we are finding the correct solution. It just tells us that we find the best solution possible given this inlier set with probability 1 minus epsilon. Okay, so that's what it tells. We still need to check if this is actually a valid solution, because it might be that there was actually no possible alignment between these two scans. So the robot is completely somewhere else. So that's something we still have to consider in the front end. But the matching here, it just assumes that there is a matching and gives you the best one. Okay? The problem of RANSAC, again, is also local minima. So we can never remove this local minima, because there might be two different things which really look like the same, and due to noise or due to bad luck, you always get the wrong inlier set. So, and you ended up with the other minimum. And also it still has problems in ambiguities in the environment. The local minima, it's again harder to solve. For a RANSAC point of view, you can do more iterations, but there's never, you're never 100% sure that you remove any local minimum. So you have to kind of live with that. The part of the ambiguities in the environment, we can actually handle it outside of the matching part, and that's what I was telling you over and over. We'll see it in the second part, so we'll see it right now. We can think of ambiguity from 2 points of view. We can have a global ambiguity, and we can have also a local ambiguity. Okay? As a global ambiguity, imagine this case. Now, we have A, which is what the robot is looking right now, so it's seeing this from its point of view. And then we have B, which is one possible places that was before in the past, that looks like this. And then we have an uncertainty of A, which is that big. Now, if you look at this part and this part, they actually look very similar. Okay, so you can say, oh, they actually align pretty well. There is this kind of kink here which aligns with that. There is this kind of, I don't know, strange shape that aligns with the strange shape. There are some furniture, maybe it's an indoor environment that aligns with some furniture here. Okay, so it looks actually quite good, and you will tend to say this is the exact same place. Okay, do you agree? How many of you agrees on that? Yeah, yeah. So, but I mean, what if there is exactly the same copy of A inside there? Okay. So the thing here is that this might also not be the same place, and the reason is that I have a lot of uncertainty into A, and I'm just looking at B. So I know in some way, or you can say with high probability, I know that A is somewhere inside here. Okay. But I don't know specifically where it is, but I know it should be like one place only, cannot be multiple places, there cannot be that teleports or there's some wormhole or time, space, whatever thing. So it must be somewhere in here and only in one place. And therefore, if I don't know how the environment looks like in this part, I only know a small part here, it's hard to be sure that this is the right decision. Okay, and if you now open up the whole environment at the same time, you can see that this is an environment which has a lot of repetitive structures, and actually the real place where A is this one, and those are just other hypotheses which are very likely from an appearance point of view, but they are not likely from a global matching point of view. Okay, so they locally looks very nice, but globally they don't. And the way of dealing with that is related to the fact that we want to be sure that A can only be in one specific place here. So now I see a different case where we have a very lower uncertainty into A's. So we know that A must be around in this area, and if we take this place here, we put it back in, we know that there is no other possible location within this area where it can be. Okay, so then we are sure that this is unambiguous globally, and it's what is said in the literature to be global sufficient. Okay, now the assumption here is that we are very good in estimating the uncertainty, okay, which might not be the case, but in principle the idea is if the more uncertain you are, the bigger your data or the larger the part of the environment that you look at must be in order to be sure that you are back in the same place. Okay, so if you don't, if you just focus on very local reasoning, you are prone to mistake. Okay, so that's one part on the global sufficiency. The second thing is it's the local part of the ambiguity. Okay, so you can also be local ambiguous, and this is what's called the picket fence problem in literature, where you have very self-similar looking environment. So it's called the picket fence because imagine like you have a fence and there's just a lot of picket in this fence, and if you have a laser or whichever sensor you have, you will always see the same repetitive structure one after each other. Okay, so it's very hard to align around this fence if the only thing you see is the fence itself. And here, even if we know that A is in here, and even if we can put all A in there, so we are sure that globally there is no other place, but locally we can still move it around, and we can still have different different potential estimate for that. Okay, although the size of A is bigger than the size of where A can be. Okay, so that's like the local problem. So in order to be sure that a match is accepted, there is, we want to have these two criteria, and these actually are being developed by Edwin Olson. It's all second part is something taken from his work. And he defines these two criteria. So a match must be global sufficient. Therefore, it means that there is no possible disjoint match within the uncertainty. So the size of the environment I'm comparing is at least half the size of the uncertainty in some way, so there cannot be another copy of it inside. And also local unambiguous, so that there are no overlapping matches. So either A is either there or completely somewhere else. Okay, so it cannot be that I have possible local matches. If both are satisfied, then we can say this is a good match, I'm happy with that, I keep it. And I put it into my graph structure to be then optimized by the backend. If you want to put this whole proposal or this whole approach together, you design 3 main phases. So 4, let's say, but the first one is the usual one. You just have a post matcher. So it takes 2 scans, matches, and it gets a solution. So it does it for all the poses within the uncertainty. So what we've seen so far. And in this case, it does it with the correlative scan matcher, but you can use anything that you have for matching the clouds. Just need to have a transformation and uncertainty. And then what he does is, he first does a topological grouping. The idea of topological grouping means that if there is a lot of close by matchings, like this, these are all belonging to one group, because they all somehow tells us the same information. This pose is somewhere around this area, okay? And after that, it does something called single cluster graph partitioning. So it takes all these measurements, this association, and tries to find which is the maximum subset of them that is consistent to each other. Okay? And this is to address the second criteria, which is the local unambiguity. Okay? Then, once this passed the test, it does a global ambiguity test where it checks for the global uncertainty and the size of the local map, where local map will be the size of the topological grouping. So will be, let's say, the number of these nodes and how big this is with respect to how big the uncertainty of A is. Okay? Now, the first one is for the second criterion, and the second one is for the first criterion. Now, we're going to look at all of them individually. So the topological grouping, as I said, is the robot goes around and at some point comes here, and there's a lot of matchings with these poses here, then goes around again, and there's a lot of matches with these poses again. And this part here is a first group, this part here is a second group. The way you handle this is on a threshold based, so whenever you get one match, you just go around here and you consider n left and right, where n is computed according to the odometry uncertainty, so how far you can go left and right. And you do it for both cases, so for each of this match, you do it for both cases. And when there is no match any longer, you just remove them. So in this case, the poses which are in this group will be these 5 here, plus these 3 here. And down here will be the same, like 1, 2, 3, 4, 5, this 6, and this 4. Okay? So they all belong to one group. So basically the idea is that what defines the grouping is the number of measurements, so the solution that comes out from the matching part, plus the neighborhood that is between them from the odometry chain. Okay? And each of this group then votes somehow for potential association. So for each of this group, we then ask these 2 questions. Is it locally unambiguous? Is it globally unambiguous? Okay? Question? Okay. Now, the goal of having locally unambiguous matches is that we want to remove measurements that somehow they are not consistent to each other. Okay? By not being consistent means that they end up in a different solution. There might be outliers. There might be this picket fence problem. So we want to remove these matchings that do not agree. And we want to visually go from something like this, where we have a lot of poses here and there and wrong matches, to something like this, where everything is very nicely aligned at the end. How we do it? We do it statistically. So the whole concept here is that if I have these two measurements, if they agree to each other, it means that whenever I go from one pose and I go all around the transformation, I should end up in the same pose. Okay? So if I go back in the same pose, it means that the transformation that brings me, or the wormhole that brings me from here to there, and the one that brings me back, that must be consistent. Okay? So imagine like this. I have these two hypotheses, Hi and Hj. Okay? And I know that this path here from the odometry is quite consistent. They're very close by, so there's no mistake in this. And there's also no mistake in here. So these two paths are actually the same. Now, if I go from here to there, using the odometry, then I go here from the measurement, I go forward with the odometry, and I go back with the other measurement. If those two are one the inverse of each other with respect to the different transformation, then I should end up in the same place. Okay? If those are not, then I am in the wrong place, and nothing matches. I don't know if it makes sense, but it's like, imagine this as elevators. I go one floor up, I go one floor down, they are consistent. But if one is I go one floor up and this is I go 2 floors down, then they are not consistent any longer. No? Kind of the idea. Now, if you define then a measure of consistency between each of these measurements in one topological group, then you can define which is the most consistent group there. And the idea here is that I have this hypothesis set from my topological group. These are all the measurements that are association. I pick up any two of them and I compute a consistency measure in a matrix A. And this consistency measure is how different from the identity is the resulting transformation on the loop. Okay? So it's like a prior to say the transformation should be, the translation should be 0, the angle should be 0. I compute the loop, and then I check how those are far away from the identity transformation, and this gives me a certain level of probability or a likelihood that the loop between I and using I and j is different than the identity. Okay? Once you have this, you want to look for the measurements that have to the highest number of measurements that are actually consistent with each other. Okay? This you can see it as a problem where you have an indicator vector v, okay, that tells you this measurement is good, this measurement is not good. No? So like 1 if it's correct, 0 if it's incorrect. And you want to find the highest number of correct matches. You can cast it in terms of a problem where you say, I multiply this vector by the matrix I found, and the vector itself, so I can get a scalar. So I have a quadratic form there. And the idea here is that this basically, there is a 1 and a 1. It's just a way of selecting elements from this matrix. Okay? So this V transpose AV, it's basically summing up all the elements of ij whenever V says as 1 in I and j. Okay? So you can see it when you multiply V transpose A, you're basically summing up everything where I is 1 altogether. And then when you multiply on the other side, you sum it up whatever from this resulting vector as j to 1. Okay? So in principle, I went back. In principle, these things here sums up everything which is in the matrix where I and j are different than 0. You normalize it by the number of elements that you have there, and this gives you a score of pairwise consistency. So in principle, if this one selects inconsistent matches, A is very high, this is very high. If those two as consistent matches, A is low, this gets low. And you also want to have, since you have a normalization here, whenever you select not many of this V, then the normalization terms will put the things up again, because you will have some division by 0, by something close to 0, so you will end up in a you will still want to have the maximum number of elements in here. The problem of this formulation is that if you stick on 1, 0, so if you stick on the indicator variables in the vector, you end up in a problem which is NP-hard. It's one is called the densest subgraph problem. So you want to find a subgraph which is the densest in a sense of the amount, the weight in the edges is the highest. Okay. To have a rough, so to have a solution for that, what people can do is to just relax the problem, the original problem. So it's the typical trick for going from NP-hard to something which is tractable but an approximation. You just remove the fact that V, the elements of V must be either 0 or 1. You just say the elements of V can be any number, or you can simply say it can be any number between 0 and 1. Okay? Now, if you take this with the continuous problem, you have a continuous estimation problem. It's non-convex, but that's a very nice form, because if we take the gradient and we put it to 0, we end up in an eigenvalue problem. So this one is an eigenvalue problem. We can easily derive it if you want. We can just, so we assume A is symmetric, so the derivative gets actually easier. But let's say we take the gradient of the thing with respect to V. So the upper part, this will be a V. And then we need to multiply by the thing down, so times V transpose V. We take the minus and the other way around. So we have then we have V transpose A V V. Take the derivative of the down things, and we divide them by V transpose V square. No? So that's just the gradient of this function. Now we can see that there is this part here where we have this together. Okay, so can be eliminated. And if we now put this with one part of that, this is actually equal to the lambda V. No? Because we can split it, let's do it step by step. We can split it in AV V transpose V divided by V transpose V square minus V transpose AV divided by V transpose V times V divided by V transpose V. No? If you look at this in this way. Right? So this basically means that we have this and that can simplify. This is our original function, so it's just lambda V, so it's a lambda. And since we are trying to maximize it, this is a scalar, this is a scalar. We are looking for a vector which is normalized, so we know that the size of this vector is 1. We just look for the versor. So this is actually equal to 1, this is equal to 1, and this ends up in AV minus lambda V, which is, yeah, what I wrote here. This must be equal to 0, and you just end up in the typical eigenvalue problem down there. Okay? We know how to solve this. There's a lot of tools for doing this. One way is to do the SVD or using any eigenvalue solver for that. Once we have this eigenvalue, we can take the one with the eigenvectors because we want to find the highest lambda. No? That was the one we were looking for, the lambda with the highest value. So we take the highest lambda, and this will be the subset, somehow close to the idea of the subset of most consistent measurements. Now, we want to also be sure that there is no picket fencing problem. So we want to be sure that the second best hypothesis is actually very low. Because if the first and the second best hypothesis are roughly the same, it means that they are very ambiguous locally. No? It means that this set of measurements can have two different solutions. They all somehow the same, or they are both very highly likely. Okay? So we check then the ratio between the first and the second eigenvalue. If this is quite high, way above 1, then we are sure that the first hypothesis is way better than the second one. And if this is close to 1, then we know that there are some picket fencing problem. We know that there are some local ambiguity in local ambiguity around this area here. Okay? Now, the problem which is left is this last one, where we want to discretize V1. Okay? The problem there is that we want to go back from something which is between 0 and 1, normalized vector, to something which is 0 or 1. The main trouble we have here is to find the threshold for which we can say if everything is below this threshold, you get 0. And if everything is above this threshold, you get 1 into V. There are two ways of doing it. One is you try to find the discretized vector that is the most orthogonal, the most parallel to V1. Okay? So you want to keep the direction. So you take the dot product of the discretized vector with the real vector, and you try to put it as high as possible. And the other one is just you go back on the original formulation. That's what we wanted to find, and you try to find the V that maximizes that. Okay. The way we search for the V is we just have one parameter. It's this threshold, and we can just do binary search, or we can do grid search, any type of search that you want to do. Okay. So you just start from. We know for sure this threshold must be between 0 and 1 because the vector is normalized, so everything must be between 0 and 1 as elements of this vector. You first start with 0.5, and then you check how good it is. Then you go to 0.25, and you look if you have to go left or right, and you just do a binary search in that, do grid search, anything that you want to do for a search on the threshold. Okay? Once you find the threshold and maximize that, you have your discretization at hand. And this basically means that some of the measurements stays and some of the measurements are actually gone. Okay? That's for the first part, so the second criteria on local unambiguity. And the other one is the global uniqueness or global sufficiency. And the idea here is that we want to really look for copies of A if they can be arranged within this, so that you can find multiple possible arrangements of this inside. But what we actually really do is that we check the dimensions of A, and we check it in terms of like an ellipsoid, kind of the dimension of the axis. And then we check which are the axes of the uncertainty where A can be. And we look if each axis aligned is at least half of that. Okay? And if it's at least half of that, it means that there cannot be any other copies around here. You can do some more coarse approximation. You can just take the maximum, you check in with the maximum without doing the alignment and so on. But in principle, the idea is to try to find some very quick way of saying, is this big enough? And big enough is like the area spanned by this local match with respect to the area spanned by the uncertainty. Okay? And that's what we're trying to do. So this is it for the front end part. So what we've seen today is how to match data within each other, how to select which are potential candidates to be matched from a previous solution of a graph-based LAM. So how to compute the uncertainties and how to check if the current visual, the current data, sensor data can be matched of something considering the uncertainty. We also show different ways of matching, so from dense matching, point-to-point matching, feature-based matching, and also how to deal outside of the matching routines on problems of ambiguity in terms of local ambiguity and also in terms of global ambiguity. Bit of literature, the part on the spectral clustering, so this global and local ambiguity, you find in this paper here. And here it's something that I did. So as an example of feature that you can detect for 2D laser data, so how you can actually handle this 2D range data and to find points and how to describe these points. So I'm not putting it into the exam at all, but it's a nice read if you're interested in this kind of features. There are some pointers in here also on how people did it in vision, so how they analyze features for camera images and several experiments. You can also go through that and read about that. So this is for the lecture today. Do you have any question on the front end? No? Okay, so I can just then do a brief summary of the class, and then we can say goodbye. So, so what we studied during this whole class is this problem here. It's called LAM for simultaneous localization and mapping. And in some way you can summarize it in, given that I have some measurements of the world and some measurements of how the robot moved in the world from his own sensor data, I want to know how the world looked like, so this M here, and I also want to know where the robot is in this world, or how the robot navigates in the world, so where did he collect all this information, okay? And we've seen different ways of answering this problem here. I call it a problem because we want to find the posterior, so it's an inference problem. We want to find the posterior information given some data that we acquire. We have seen this as a chicken and egg problem because we know that if we have a map, localization is easy. If you're localized, mapping is easy. And now we have this interplay of localization and mapping together that just go one after each other. That's why it's defined as a chicken and egg problem, and that's where also a lot of difficulties come from. And we have seen three main paradigms: a Kalman filter, a particle filter, and a graph-based. They have all of them pros and cons. The Kalman filter is very quick to implement. It has an assumption of unimodal errors, Gaussian distributed errors, and linear or close to linear sensor model and motion models. Okay, it's also optimal in the linear case, but it is not optimal in the nonlinear case. And we have seen ways of making it efficient. So it's normally not that efficient, but we have seen that if you can exploit sparsity, like when you do the extend sparse information filter, you can get into a very efficient implementation for the Kalman filter. The Kalman filter also connects with the graph-based. I'm just jumping a bit there for a few reasons. One is that the assumption of the graph-based is similar to the assumption of a Kalman filter-based. We have Gaussian errors. We have, in a generic, or let's say in the simplest implementation, we have unimodal measurements, and we deal with linearization. So you remember the Kalman filter, the extended Kalman filter, you need to relinearize, and then you solve the linear problem. And the graph-based, also we have these linearization steps. The interesting thing is that if we have a linear problem in the graph-based, under all the assumption of Gaussian noise and everything, so we have a linear least squares problem, and we use a Kalman filter, they end up in the same solution. The reason is that the Kalman filter is the optimal recursive solution for a full batch least squares problem. Okay? If we are nonlinear, that's not true any longer. The reason being that when we do nonlinear least squares, we relinearize everything, while when we do an extended Kalman filter, we just linearize at the beginning, the first time we get the measurements, and then we forget about it. So we stick with that linearization point. That's the main difference in that. But for the rest, they are very, very similar and very related. The particle filter is on a completely different way. It goes more on the sampling approach. There is no implicit minimization of a certain error function, but it goes in estimating the density out of samples. Okay, so this whole posterior density is a weighted sum of Dirac delta, so individual samples. You get the sampling part, which is from a proposal distribution, and there is a weight computation according to the important sampling principle, and then there is a selection based on the sample set, which is the candidate samples for that. Okay, so it's slightly different. It has pros and cons. It's quite efficient, and it has a very nice scheme for doing data association inside, because each particle can have each individual data association, which is very easy or very simple or naive approach. But then when you put all the particles together, you have a very complex data association approach with multi-hypotheses within that. Nevertheless, they all work on the same embedded graphical models behind, where we define our conditional distribution. So we have a part which is observed, which is the odometry and the measurements of the outside world, and there is a part which is unknown. Okay, and we have seen what's called the full slam, where we have an unknown here, and we want to estimate the full unknown part on the robot trajectory. And we have seen also a non-line slam, where we still have an unknown here. Unknown is the white circle, but we're only interested in estimating this one, so we are marginalizing out all the previous poses. Okay, and we have seen that Kalman filter approaches, they address this problem, and particle filter or graph-based, they mostly address this problem. So what you should have learned during this class, I hope all of that, some idea on how the problem is formulated, what is the problem, how to build maps, both if you have landmarks and if you have grids, a set of different approaches over the time. So they were the state of the art according to their individual time. This is around the 90s, towards the end of the 90s, both of them, the 2000s, and this part here, they're actually connected. But at some point, they just say, okay, let's just work on the optimization part, forget this, let's assume someone tells us everything, and then they start to realize that this is an important part as well, and then people start working on that. You should have some experience in programming in Octave during the exercise, and I hope you can now understand SLAM paper. So if you download one, you at least get an idea when they talk about the literature, what is this, what is that, get a bit the main formulation, the main ideas behind. There's a lot of that we didn't cover. The field goes, every year is probably like 10 new papers, so it's very hard to cover completely, but this is a nice overview so that you can get the latest work and understand that. We did some, so I told you a bit briefly a comparison of this. So the first part here is belonging to the Kalman filter family, where we have the linear case, the different non-linearities. So the way to handle it, first order approximation, second order approximation. Also seeing the connection between these two guys and the graph-based Gauss-Newton or Leven-Marquardt or companies. These are different algorithms for minimizing this objective. The Kalman filter family minimizes the same objective, but in a different way, in an iterative fashion. You have seen some part here on the safe, where you actually consider the inverse filter. And if you now try to get a bit of connections behind, there was something that says sparsity helps us. Here we have a sparse graph. This was working on the information matrix part. Each measurement has its own information matrix. We have a connection between the graph structure and the information matrix of the graphical models. So this is like you can see it as a path in some way that then comes back here. No? There's a lot of things together. If you remember when we talk about safe, at some point we said one problem is to get the mean out of it, and we do some minimization there. Actually, what we are doing is exactly some steps of that. So they are very, very related. And then we've seen the particle filter family, fast-lam and grid-based fast-lam or RBPF-SLAM, where we've seen that when we go from the Monte Carlo from the localization to the SLAM part, space becomes a problem because you have a huge map, so you need to reduce the number of samples, and you've seen how to do this, how to choose a good proposal, how to choose the optimal proposal, how this influences the whole algorithm. Do you think there is something left open, some problem that we still need to address in the field? This is more like towards you if you have any idea. There is a slide coming with the list. The question is how many from the list you can match. Are we done? Can we now go with the car around and build the map of the world? Can we handle, if you go to a train station at rush hour, do you think what I explained you can build the map of the train station? Yes, no?
I think the dynamic environment can be modeled by this.
I haven't told you anything about dynamic environments. You can try. If you do data association correctly, yes, but it's going to be very hard to do data association correctly. The second thing is, what happens if I'm here, I go downstairs, I come up here, and now instead of having all these tables, there is a stage and there is a band playing up here. Is it the same place or not? Yeah. So these are the things that are still a bit open. No? There are some more semantic or more philosophical questions that are not being answered, and they all are about, am I lost or is the world changing? That's like one first question to ask. Because from the point of view of yourself, it's the same. It's just that I believe I'm somewhere and my sensor data is telling me differently. Now, who's right? Am I right or is the sensor data right? And it's hard to find a compromise between that. No? So this is, for instance, one problem. You can just open the list. But that's, for instance, here, dynamic and systematically change, or if I'm outdoor, there are some seasonal changes. You know, like in winter, everything is white. In summer, everything is green. So if you just use color to distinguish if you're in the same place, it's not going to work. So a lot of problems from the, let's say, a lot of things from the geometric point of view, from the pure measurement and the reconstruction and the estimation part is actually well understood. What's the main problem is the building of the graph. So how to handle data association, how to handle ambiguity, how to handle also like lifelong operations where the robot is running forever and sometimes they have to change things. Maybe there is too much data, you cannot store the data. So these are all like problems, or when you have constraints that you have to get rid of something, and which is the best way of getting rid of something, and which is a metric that can tell you, I don't know, I'm only able to do 10 computations per second. Which are the right computations to do? And then you have to think about it. Do I prefer to be well localized? Do I prefer to have a good environment? How many landmarks, how many poses can I store? This whole problem here. Prior knowledge, sharing maps between the robots, or on another point of view, which is related, but it's more related to localization, is can I use any information that I have to help me? Like now there's maps of the world. I can take a phone and there is Google Map and I can see where I am. Can a robot use that? Can a robot learn how to extract information from that and either use this information to improve its mapping or just use this map and how to handle these all things together? Okay, so there's a lot of things open, and these are just for the SLAM. You can also have some sensor-related issue. Sensors are not good. There is no light for vision. So there's a lot of problems. Maybe there is another sensor coming up, so we can just now to work for a new sensor. There is actually some things called dynamic vision sensor. I don't know if you know them, but they are actually cameras that goes at a lot of hertz. I will say 1,000, I'm not 100% sure. But instead of giving you the full image, they will just give you the gradient of the image. So they just take image differences between the previous frame and the next frame, and it just spikes you. So you basically only get the differences, and what you're seeing is just small lines or small pixels here and there in your image. And so on one side, you have super fast sensors that you can use to do a lot of crazy high dynamic movements if you have a, I don't know, a flying robot. But then you have very limited information each time. So building a map out of this, it's not trivial. Anyway, this is everything from the lecture. I wish you good luck. The class is over. Normal situations, I would say, see you next year, or like tell the others, I would say, I wish to see you next year, because it means that you actually have passed the exam. And I wish all of you to pass the exam with good grades. I would say, you think that it depends on me. Actually, it does not depend on me. It depends on you. Yes?
So, can you tell the time of the exam, because only the date was given?
Yeah, the thing is that the date is given because according to, so if I put slots, then people might say I come in the early slots and then in the later slots. And then I have half day with a lot of empty slots. And to avoid that, we first collect the number of people, and then we do the schedule for the day so that every student is one after each other. Now, the question is, I also do not know the schedule. I have to talk with Frau Schneider. And I hope everything will be fixed by in a few days. So I'm going to ask her. Because otherwise it will be complicated to... it's unfair if you have to come at 8 in the morning and then have an exam at 4 in the afternoon. That would be a bit unfair. So I will contact the Prüfungsamt and check about that so that we can make a schedule daily. So she told me she will give me the protocol with everything. She hasn't done it yet. I'm gonna push and see what's happening.
How long is the exam?
The exam is 20 to 25 minutes. Depends on how quick you answer and everything. And we'll see. Sometimes maximum is 30 minutes. I cannot have an oral exam more than 30 minutes. It's just university's regulation. So the goal is around 20, 25, and we'll see.
So do we have to remember every step of these slams or for the exam?
You have to remember everything I told you, even more. So I cannot tell you, don't study this for the exam. That's really like something I cannot say. So the only thing I can officially say is you have to study everything.
No, I have to study everything. What are the things that I have to remember? Like I have to remember the steps of the slam or things like that. Like if there are 20, 30 steps of the slam, the grid map or something like that. So do I have to remember all of them in the sequence?
So
All the
I cannot tell you. Okay. In principle, you have to remember everything, and actually, you don't have to remember everything. You have to know everything. It's a different thing. So the whole point of an exam, an examination, is to understand how much you learned during the class. It's not to understand how much you memorized during the class. Okay? So you have to show me that if I ask you something, you have to show me that you understood that and you learned that. How you show it, it's up to you. You just have to convince me. Does it answer somehow? Sorry.
We can say
Yeah, can say that.